So the system then gets reduced down to this thing and the constraints. Right. Yes, Shannon.
Just thinking about having n in one of them and like the n is sort of very small than n in the other.
Yeah. So there are n minus 1 different constraints here, as m ranges from 1 to n minus 1,
Okay.
right? And then there's one more condition. There's one more equation. So in total, there are n equations.
Okay.
Right. So right at each stage, at each of the n minus 1 stages, right, when we take the first derivative down to the n minus 1th derivative, at each point we impose a condition that wipes out the second terms. Okay, we wipe out the second terms, we wipe out the second terms. These are those conditions. You know, these are all the set the sum of the second terms equal to 0. Yeah.
So if n goes to n minus 1, why is that g of t and not 0?
So this is what you get when you take these guys, and this, and you take these guys and plug it back into the non-homogeneous equation. Okay, that doesn't have to do with this. This is a separate set of constraints, right? So. So what are we doing here? All we're doing here is we're calculating the derivatives. The first derivative, the second derivative, the third, down to the n minus 1 derivative. That's these guys. Here's the nth derivative, and then we plug everything back into the non-homogeneous equation. Okay. And along the way, we imposed a bunch of conditions. Okay. We hold the conditions on the side. Right. We plug these things back into the non-homogeneous equation. A miracle occurs. Right. Cancellation. Tremendous cancellation occurs, and we end up with just this. Okay. So what we end up in the end with is that this equation reduces down to this equation. Okay. But along the way, we also have some constraints. So we need to solve both the constraints and that equation to figure out what the UIs are. Is this clear? It's a bit tricky. I mean, it's a bit intricate, but it's not anything more than what we did before. Yeah, Christy.
Just clarification. So when we're plugging in everything, we're plugging in all the derivatives.
Yes.
Are we doing n minus 1 or n?
N. Right.
N. Okay.
So these are the first n minus 1 guys, and then there's the nth part there.
Okay.
Right.
So we're ignoring the n stuff over there. That was just the stuff.
These we're going what?
Okay. Never mind. I got it.
These guys are the derivatives from the function itself down to
N minus.
n minus 1. Yeah. To the n minus 1 derivative. Right, plug everything. Okay. Let me step one step forward, and I think you'll be a little bit happier. So what this boils down to is we obtain the following system. So I'm going to rewrite the constraints and the following system of equations that the UI prime must satisfy. And here it is. We get that y1 u1 prime plus y2 u2 prime plus yn un prime is equal to 0. Right? That 0, you want y1 u1 prime plus y2 u2 prime plus y3 u2 prime. So all equal to 0. Right?
Would it just go to n minus 1, not n?
I'm sorry?
Wouldn't that then just go to n minus 1, not n? Or would it still go to n?
It will still go to that.
Okay.
Right, yeah, see, we're going from, I goes from 1 to n still. Right, right, because here's the condition right here.
Oh, okay.
Right, here's the condition, right, we're taking the sum from from I equals 1 to n. The sum of the second terms has to be equal to 0. So all I'm doing is writing this constraint. I'm just rewriting this constraint. Does everyone see that those two are the same thing? That's right. I just changed the order. Y1 u1 prime, y2 u2 prime, y3 u3 prime up to yn un prime. Right, and now I'm going to write the second constraint. Right? The second constraint will be y1 prime u1 prime plus y2 prime u2 prime plus yn prime un prime. Right, and then I'm going to go so I'll have right, n minus 1 conditions here. Right, those are the constraints. These guys are the constraints, and then I'm going to have that last thing, the last thing that comes out of the equation, right? y1 n minus 1 u1 prime plus y n minus 1 un prime equals g. That is what the equation reduced to. Right? So you've got the constraints and you've got the reduced equation. Okay. Okay. And what do you see about this? Yeah, Blake.
Oh, sorry, I guess one question I have is like, what would the last n minus 1 condition constraint look like?
Just erase what I would. Let me.
If we were
So
just
the last
clarifying,
one is going to be the last one is going to be
because it almost looks identical to like what you just wrote, except equals 0 instead of equals g.
so this one should go to u2, wait. So that one should have gone from 0 to n minus, I'm sorry, it should have gone from 0 to n minus 2. So, so this one should be, right, y1 n minus 2, right, y1 n minus 2, u1 prime plus y and n minus 2, u1 prime. So the n minus 1 conditions, right, going from 0 to n minus 2.
Okay.
Right, going from 0 to n minus 2.
So then, like, just going back a little bit, then the m should go from 0 to n minus 2.
That's right, sorry. The m should have gone from 0 to n minus 2. Okay. Okay, so here we have an n by n system, right? And what do you see about the system? That we can solve for the ui prime if what happens? Right, if we write this as a matrix, right, this is u1, u2, y1, y2, yn, y1 prime, y2 prime, yn prime, all the way down to y1, n minus 1, y2, n minus 1, yn, n minus 1, right, times u1 prime, u2 prime, un prime, right, equals 0, 0, 0, 0, 0, g. Right? And when can we solve this?
Wait, so the bottom one in the matrix is, oh, it's so it equals G, okay.
When can we solve this? Or can we solve this? How do we know we can solve this? So, which we can solve because
Did you just say the determinant's not zero?
if the determinant, as long as the determinant is not zero, and it is because the determinant is a Wronskian, right? Right? The determinant is a Wronskian for these for the fundamental set of solutions of a homogeneous equation. Those guys are linearly independent, and so we know that Wronskian is non-zero. Which we can solve since we know that the Wronskian is not zero. Philip?
Can you repeat why the things up there?
Sure. This is the Wronskian for the fundamental set of solutions for the homogeneous equation, right? The Wronskian is non-zero if and only if those guys are linearly independent. Those guys are linearly independent because they're the fundamental set of solutions. So that's Christy, yes?
Could you explain one more time why we're putting that last, the reduced equation into that? Like, is the reduced equation right there
Yeah.
coming out of, could you explain the relation between that and the, all the?
Sure. So remember what we were doing, we assumed that the solution had a particular form, and then we basically plugged that form back into the non-homogeneous equation,
Okay.
okay? With some constraints assumed. These guys here are the constraints. Okay, these guys here are the constraints. When we plugged it back in, we ended up with this equation. So
We plug the constraints back into.
when we plugged summation ui back into the non-homogeneous equation.
Okay.
With the constraints
Oh, we
assumed,
got G, because that was.
then we ended up with this. Then we ended up with this thing.
Okay. And we want a solution to all of those
Yes.
constraints
Yes.
and
Yes.
the original problem.
Yes. So we've got to solve
G,
all of
so
these.
that's why we're making everything, okay.
Yeah, we've got to solve all of these. Right? The UIs have to satisfy all of these in order to work. Right? Okay, I guess we don't have enough time, but let me. So, what's going to happen at this point? What are we going to do? We're not going to remember this. We're doing something equally bad, or in some sense worse. We're going to use the adjoint matrix. Okay, that is, we're going to invert. We're going to this matrix. We're going to call B, and then we're going to invert it. Right? We'll hit both sides with B inverse. We'll end up with U1, U2, blah, blah, down to UN prime equals B inverse times 0,0001 times the number G, right, times the scalar G. Okay, and so the problem will be, what is this B1 inverse? What is this B inverse? And for those of you who want to know, want to refresh your linear algebra, here's something you should recall, that if you take that the inverse matrix can be expressed as 1 over the determinant times the adjoint matrix of B. Times the adjoint matrix of B. That is, we know exactly what the inverse matrix looks like. It is basically the adjoint matrix times some number, right? Where the adjoint matrix, you recall, I'll just put up some terms for people who are not familiar. This is the transpose of the cofactor matrix. Cofactor matrix of B. Okay. And that's what we're going to use to finish this up.